Hi, HMS modelers. This is Matt Fleming, and I work at the Hydrologic Engineering Center. And in this video, I'm going to talk about the recession baseflow method. On this slide, you can see the equation that's used to model flow, or the recession curve for a hydrograph, whenever the recession baseflow method is specified for a subbasin element within a basin model. First, let's look at the figure on the right. You can see the red line, so that represents the recession portion of the receding limb of the hydrograph. And so the equation on the left, this exponential decay type equation, that's the equation that the program is going to use to model this decay or this recession limb of a hydrograph. And so let's look at the equation here. So we have Q sub t, that's the flow at time t, so at some time in the future. It is equal to the flow at the beginning of the recession curve. So if we look back at the figure right here, the flow at the beginning would be the flow at the point of inflection. So we choose that flow, or the program's going to choose that flow for us based on some user specification. And then that's going to be the beginning of the recession curve, and then that flow is going to be multiplied by an exponential decay constant. So this is a parameter that you would have to define within the user interface. And then that exponential decay constant, it is raised to a power, and that's based on the time. So what time in the future is it? And for example, if we had an exponential decay constant of 0.5, then 2 or 3 days into the future, that 0.5 would be raised to a power based on hours or days. And you can see, well, any value between 0 and 1, if that's going to be raised to a power, then of course that value is going to be much smaller. And now you can start seeing why this, or how this equation could be used to estimate a future flow given no precipitation. We're just letting the flow that fell onto the watershed either run off the watershed or percolate into the soil and then back onto the land surface and then out of the watershed. That was the equation the program's going to use. The figure on this slide shows the user interface and then the information that the user is supposed to specify in order for the software to use that equation. And we can see this is the component editor right here for a subbasin element. I have the baseflow tab selected right here. And you can see the different parameters or initial conditions also that are required for the recession method. The first one here is the initial discharge, and I have a slide in the next couple of minutes that goes into a little more detail, but you must specify the initial condition at the very beginning of the simulation. So for the very first time step, how much base flow is in the system. The next parameter is that recession constant. So back to this original equation, that k value, that's the exponential decay constant. The user has to specify this recession constant. And then finally, this is a threshold parameter. So what is, so this threshold parameter, this is what the program uses to begin the exponential recession on the receding limb. So you can either specify a threshold flow or a ratio to peak. This slide shows a little more information about that recession constant. If you look at the figure on the right, upper right, you can see that I've highlighted the recession constant right here. And in the figure in the lower right, this is where I've computed 3 different simulations, and each of those 3 different simulations, I varied that recession constant so that we could see or isolate the impacts of that recession constant on the receding limb of the hydrograph. You can see here the solid blue line. This shows us a recession constant of 0.1 and how that receding limb would look. The dashed line, the larger dashed line, has a recession constant of 0.5, and then the smaller dashed line has a recession constant of 0.9. So what you can see from these 3 simulations, a recession constant closer to 0, that means that that receding limb is going to make it to a value of 0 CFS much faster compared to a recession constant that is closer to a value of 1. In that case, that recession curve is going to be a lot flatter. You can see the slope is much milder as that recession constant is closer to a value of 1. Let's see here, the two other notes that I have on this slide. It's not possible to model both inner flow and that slower responding groundwater flow component. You would have to look at your hydrograph or your watershed and look at what the major contributor to the base flow is. Is it groundwater flow or inner flow? And then either choose one of those or do your best to approximate both of those. But you can see the challenge here, right? You only have one recession constant to describe the base flow recession. And then finally right here, you can see this last bullet. Notice how the recession constant had little impacts on the peak flow right here. If we did have a second peak, so if we were doing more of a continuous simulation, then yes, that recession constant would impact that secondary peak. But for this single event, this recession constant did not impact the initial or the larger peak flood value right here. On this next slide, I have another example to isolate how a different parameter is going to impact the base flow recession. This slide, we're going to focus on the ratio to peak or the threshold. So this is the threshold where the program is going to turn on that recession limb or that base flow portion of the hydrograph. And in HMS, you're going to have two options. You have a ratio to peak option, or you also have a discharge option where you can specify the discharge or that threshold when the recession curve turns on. I usually like to use the ratio to peak option because that one is going to be independent across a basin model. So if you had 20 sub-basin elements, for the most part, once you found a ratio to peak that worked for a couple of locations, then it's generally applicable to the subbasins across the model. Let's see here. Let me look at this second bullet. You can see, here's the example of what the ratio to peak actually means. So if I had a ratio to peak value of 0.5, well, if the peak flow in my example was 100 CFS, then the program would turn on that receding limb when the recession portion of the hydrograph when it hit 50 CFS. And then the program would transition from direct runoff using the unit hydrograph to only that recession curve. So you can see in this example, I have three different ratio to peak values: a ratio to peak of 0.1, a ratio to peak of 0.5, and then a ratio to peak of 0.9. And you can see the peak flow in this example, let's say it's about 7,500 CFS. And so a ratio to peak of 0.1 means that recession curve, that recession constant in my example is 0.5, that recession curve is going to turn on when the falling limb of the hydrograph reaches about 750 CFS. And you can see that right here. The second example, 0.5 is the ratio to peak. Well, you can see, well, when that recession or the falling limb of the hydrograph is around 3,500 CFS, then the recession curve turns on. And then a ratio to peak of 0.9, well, we don't get very far down the falling limb of the hydrograph before the recession curve turns on. All right, next slide. So now we're going to talk about the initial discharge, and you have two different options for specifying the initial discharge. You have a discharge per area, and then you also have the discharge option. So if you do choose the discharge per area, you would specify a rate per area. And you can see in the user interface right here, CFS per square mile. And what this means is if you have a 100 square mile watershed and you specify an initial discharge of 1 CFS per square mile, then at the very first time step of the simulation, you would have a flow value of 100 CFS. And then the recession curve would turn on at that value. Okay, one thing to note with this initial discharge, this is only the initial base flow from the subbasin element at the very first time step. After that, all the computations are going to be based on other information either within the base flow component editor here, or if you have precipitation falling on top of the subbasin, then all that information would be added to the computed flow. All right, I usually use discharge per area. Again, this one is kind of like the ratio to peak option. Discharge per area is generally consistent across the subbasins in a basin model. So if you're able to hone in on a couple of, or one discharge per area, if you have a gauge location, then you can easily set that value for other subbasins within the basin model. You notice that initial discharge per area in this example doesn't have much impact on the peak flow. That's probably because the combination of the recession constant and the initial discharge by the time that that peak flow occurred is pretty low compared to the direct runoff in this example. But in some cases, that initial discharge could have more impacts on the peak flow. So you want to make sure that you're using some kind of observations, observed flow to help you set that initial discharge. And then what I like to do is I like to be strategic when I begin the simulation. I usually try not to begin a simulation right after an antecedent storm event, because in that case, if you do, you're going to have some of that inner flow from that initial antecedent event impacting the flow for the event you're trying to model. So I usually try to find an event that's separated. Well, there's at least some separation, 2 to 3 days between events, and then begin the simulation when I know that only the groundwater portion of the baseflow hydrograph is the main portion in the channel network. And then on this slide, you can see the recession baseflow method can be used in a continuous simulation. So we have a plot from a subbasin element right here. We have our observed flow in the black line. The total computed flow is the blue line. And then the base flow contribution is in the brown dashed line. Again, the base flow is a subcomponent of the computed total flow. And you can see that when it does turn on, when that recession curve does turn on right here, the base flow is at some point about right here in this example, it is the only contributor to total runoff. And then we have that recession curve turns on, or it stays turned on right here. And then we have another event, this secondary event right here. And then at some point that threshold is triggered, that ratio to peak is used to trigger the threshold, and then that recession curve turns on a second time right here. This last bullet shows, here's another example where the recession method cannot be used to model both inner flow and the slower responding groundwater flow. You can see I've tried to approximate both, but you can see here for inner flow, I'm overestimating the runoff or the recession curve for inner flow, and then underestimating the portion of the hydrograph for the slower responding groundwater flow. So it's not going to be possible to model both, but you can do better and approximate both if you set that coefficient appropriately. And then finally on this slide, this is really important for the recession baseflow method. Again, the recession baseflow method does not conserve mass. So the program does not take into account any of the water that is lost due to infiltration or storage in the soil. With the recession baseflow method, it is strictly a curve fitting type of approach. So the program is going to find that trigger flow or that threshold flow and then turn on some recession curve. What you really must do whenever you use this recession baseflow method is you need to look at the volume of the computed hydrograph and make sure that the baseflow volume, total discharge volume, do not exceed the precipitation value. What I have in this example, this is somewhat, it could happen in different applications. This is an example where we took a model that was calibrated to some historic event. The typical flows for large floods in this subbasin were around 5,000 CFS. And then this model was applied to some extreme event that generated a peak flow over 35,000 CFS. The thing to watch out for is, well, those base flow parameters, that threshold that turned on the base flow recession, and then that recession constant, they were appropriate for smaller floods. But when you transition or attempt to use those same parameter values for extreme storms, then you could wind up in scenarios where that base flow volume results in a total discharge volume that is unrealistic. it's not appropriate to have a total, well, in most cases, it's not appropriate to have a total discharge volume that exceeds the precipitation volume. And that's what you can see in this example here. The discharge volume is 33.14 inches, but then the precipitation volume is just 32.76. So what you want to do is when you're modeling those hypothetical events that are much more extreme than the events that were used to calibrate the model, you want to make sure that those recession parameters, the coefficient, and then that ratio to peak or threshold discharge values are set appropriately so that you're not generating too much runoff during the simulation.